G'day viewers, in this episode we're going to look at a pet hate of mine, namely the popular myths surrounding Einstein's famous equation E equals mc squared. I'm not going to discuss the historical derivation of Einstein's famous equation. You can look it up for yourselves. It is well documented and available on the internet. What we're going to focus on instead is its real-world implementation and meaning. To achieve this, we're going to look at three characters: Albert Einstein, Werner Heisenberg and Edgar Buckingham. The journey begins with Einstein, so let's start with him. E equals mc squared literally states that mass and energy are equivalent. In fact, it states that they are precisely the same thing. That is, they are different sides of the same coin. However, Heisenberg's uncertainty principle has a problem with this position. How so? Well, both mass and the speed of light in a bare vacuum, c, must be known to an infinite number of decimal places. Please note that I used the expression bare vacuum, not just vacuum. C is defined for a bare vacuum, which means that it has been defined without consideration of the quantum vacuum, or more specifically, the ground state of the quantum vacuum, termed the zero-point field. Anyway, we can skip over this fact for now. I don't want to get too bogged down into the detail and meaning of the difference between a bare vacuum and a quantum vacuum. Suffice to say that a bare vacuum doesn't consider the quantum mechanical nature of fundamental reality in any way, shape or form. Of course, the quantum vacuum does, by definition. As written, E equals mc squared calls for its inputs to have exact values, not approximate values. The speed of light c nowadays is a definition, not a measurement. This means that its experimentally measured value is required to be exactly equal to its defined value, but this can never be confirmed because of the Heisenberg uncertainty principle. We would need to be able to confirm its value to an infinite number of decimal places. This is quite obviously an impossibility. Of course, the same argument applies to the value of mass in the equation. Heisenberg's uncertainty principle means that a particular magnitude of error will always be associated with any measurement. In other words, Heisenberg is saying that energy and mass are approximately equal. We can never confirm that they are exactly equal. So, how can we get around this collision of requirements? Well, this is where Edgar Buckingham steps in. If Einstein's famous equation is formulated utilising the Buckingham-Pi method, an experimental relationship function is procedurally included. The experimental relationship function relates physical reality to theoretical derivation in terms of dynamic, kinematic and geometric similarity. You can think of it as a measure of efficiency, just like the power factor associated with electrical motors. If you would like to see a formalised example of the Buckingham-Pi method, please view episode 1 on this channel. Okay, now that we have identified the reality of experimental relationship functions, what can we do about it? Let's have a look. Fortunately, the National Institute of Standards and Technology in the USA has done the hard work for us. The 2005 experimental results that they report demonstrate that the similarity between reality and theory is significant but remains inexact. In fact, to be precise, their report details the fact that the similarity between Einstein's prediction and reality was high for that specific experiment only. That is to say, different experiments may yield different values of efficiency, but it can never be 100%. Therefore, we can say with certainty that energy approximates mass. It cannot equal mass or be equivalent to mass without violating Heisenberg's uncertainty principle. Let's now summarise what this all means. The key things we've learned so far are that 1. The speed of light is defined for a bare vacuum, not a quantum vacuum. 2. The quantum vacuum contains dark energy. A bare vacuum does not, by definition. 3. Heisenberg's uncertainty principle definitively excludes the experimental confirmation of 100% efficiency. 4. The Buckingham-Pi method preserves the Heisenberg uncertainty principle and fixes Einstein's original derivation because it can never be experimentally observed without contradicting Heisenberg's uncertainty principle. 5. The only way that the contributions from Einstein, Heisenberg and Buckingham can be simultaneously reconciled is if we recognise that Einstein's original formulation denotes an approximate relationship, not an exact equality. 6. Einstein's theory of special relativity is, in fact, an experimentally verifiable impossibility. It is more accurately represented by the approximate equality displayed on screen. Okay, other than the 2005 NIST experiment we presented on the previous slide, are there any other physical examples where the experimental relationship function is a long way from unity, that is, a long way from 100% efficiency? Well, yes, actually, there are many examples of E equals mc squared being a fantastical relationship. These examples are called thermonuclear explosions. With respect to these weapons, only a small fraction of mass is directly converted into energy, and they are actually extremely inefficient mass-energy conversion processes. Typically, their experimental relationship function values will be below 1%. In other words, as mentioned on the previous slide, the 2005 NIST report is experiment specific, and E equals mc squared does not hold universally true as explicitly derived by Einstein. Once again, I repeat, Einstein's equation works for some situations better than for others, but does not work equally well in all situations. Therefore, an important takeaway from this presentation is that the popularised interpretation of an object's mass increasing to infinity as it approaches the speed of light in a bare vacuum is watered down by the non-linearity of nature and Heisenberg's uncertainty principle. The reality is that this so-called theoretical limit is an unproven assumption. Simply observing the characteristics of fundamental particles in accelerators and then extrapolating the behaviour of complex systems such as engineered machines and or materials is drawing a very long bow. For all anyone knows, the laws of physics may change radically at relativistic speeds due to undiscovered paradigms. In other words, until we have done it, we haven't done it. Please don't forget that the speed of light as presently defined does not apply to a quantum vacuum. It applies to a bare vacuum, that is, a universe without the existence of dark energy. And dark energy possesses 67 to 68% of total cosmological mass, according to the standard model of cosmology. However, we exist in a quantum vacuum. We do not exist in a bare vacuum. This means that the true cosmological speed limit may actually be less than c. Remember, the Heisenberg uncertainty principle excludes the possibility of measuring the defined value of c to an infinite number of decimal places. Lastly, an obvious question arises, that is, does the experimental relationship function approach a natural quantum limit?